Welcome back to linear algebra. In this video, we're going to be talking about diagonalization. The process of diagonalization allows us to take a complicated matrix and find a much simpler to work with matrix that we'll be able to convert back and forth through freely and will hold several properties equivalent, especially some of the properties we are interested in, involving determinant, null space, eigenvalues, and so on. So without further ado, let me get my head out of the way. And let's start with the idea of similar matrices. So the idea here is we're going to take an invertible matrix that we call P. We're going to multiply matrix A times P as well as P inverse. And that will give us a new matrix B, which we call similar. And there are several properties that are preserved in similar matrices. First of all, the determinant of these two matrices is the same. The proof there is fairly straightforward. Properties of determinants tell us that the determinant of a product of several matrices is the product of those determinants. And that the determinant of the inverse of a matrix is the reciprocal of the determinant of the original matrix. That's why determinant non-zero is so important for an invertible matrix. But now we have determinant of P and 1 over determinant of P, which cancel each other out, leaving us with the determinant of A. I would like you to try to prove for yourself that matrix A and the similar matrix B have the same null space. And I will look at the fact that A and B have the same eigenvalues. This one's a little bit more complicated than the first one I went through. But it starts off with the characteristic equation. The eigenvalues of matrix A are the solutions to the equation, the determinant of A minus lambda I is equal to 0. So the eigenvalues of matrix B come the same way, but I'm going to take it all the way back to the original eigenvalue problem. Bx equals lambda x, which is P inverse APX is equal to lambda x. And I can multiply both sides of this equation by matrix P. On the left-hand side, P times P inverse is the identity matrix. So we're left there with just A times P times X. And on the right-hand side, that scalar can go anywhere. So I can write that as lambda times P times X. Then from here, I use the same process that we used in finding the characteristic equation in the first place. Only I take it a step further and get that A minus lambda I times P times X is equal to 0. Then from here, using the property that tells us that this equation has non-trivial solutions when the determinant of A minus lambda I times P is equal to 0. And then the product, or the determinant of a product of matrices, is the product of the determinants. So the determinant of A minus lambda I times the determinant of P is equal to 0. Zero product rule tells us that's either that the determinant of A minus lambda I is equal to 0 or the determinant of P is equal to 0. But P is an invertible matrix. That was the definition that started this whole thing. And an invertible matrix has a non-zero determinant. So the determinant P equals 0 must be false, which means that we again get the characteristic equation determinant of A minus lambda I is equal to 0. There are a couple of other properties that a similar matrix can provide, giving us some really interesting tools. The one in particular that I want to look at, though, is not generally a property of similar matrices, but a specific kind of similar matrix. Matrix A is called diagonalizable if and only if there is an invertible matrix P such that P inverse times A times P is equal to some new matrix D where D is a diagonal matrix. And as we've seen several times, diagonal matrices are definitely the easiest matrices to work with. There are so many things that we might want to do with a matrix that are almost trivial with diagonal matrices and very challenging with any other kind of matrix. So if we can find a way to turn the matrix we need to work with into a diagonal matrix, our life is going to be significantly easier. The n by n matrix A, it turns out, is diagonalizable if and only if A has exactly n linearly independent eigenvectors. Remember that matrix A, an n by n matrix, has up to n eigenvalues, and each eigenvalue has one or more eigenvectors. Well, infinitely many, but a vector space of eigenvectors. Easiest case here, if we have n eigenvalues, each eigenvalue has a linearly independent eigenvector, and we're good to go. If we do not have n distinct eigenvalues, then maybe we'll get lucky and the degree or the dimension of the eigenspaces for each eigenvalue or for some of the eigenvalues are more than one, in which case one eigenvalue has multiple linearly independent eigenvectors. There's a nice proof of this theorem in the textbook. I'm not going to go through in detail because essentially the proof is a construction proof. Instead of trying to work through the construction proof, let's just go ahead and take a look at a particular example. Let's take a look at the matrix we looked at in a previous video. 0, 0, negative 2, 1, 2, 1, 1, 0, 3. We saw before that this matrix has two eigenvalues. Lambda 1 is 2, and the eigenspace corresponding to that was the span of the vectors 1, 0, negative 1 and 0, 1, 0. The other eigenvalue was 1, and it had a single eigenvector, negative 2, 1, 1. Between the two eigenvalues, here are three linearly independent eigenvectors. And because we have three linearly independent eigenvectors for a 3 by 3 matrix, this matrix must be diagonalizable. And to diagonalize a matrix, we are going to take and construct matrix P so that the columns of matrix P are these linearly independent eigenvalues or eigenvectors. So we will construct 1, 0, negative 1, 0, 1, 0, and negative 2, 1, 1, giving us a 3 by 3 matrix. In order to diagonalize, we need both P and P inverse. So a couple of different tools we can use to find an inverse matrix. My favorite is always the method of elementary row operations, Gauss-Jordan reduction. Let's start with matrix P on the left-hand side. And the identity matrix on the right-hand side. First step, row 3 plus row 1 will very conveniently give us the first column behaving nicely. Let's see, negative 1 plus 1 is 0, 0 plus 0 is 0, 1 plus negative 2 is negative 1, 1 plus 0 is 1, 0 plus 0 is 0, and 0 plus 1 is 1. From here, take the opposite of row 3. And then take row 2 minus row 3 and row 1 plus twice row 3, and that will clear out the last bit of it. So there we have it. P inverse is the matrix negative 1, 0, negative 2, 1, 1, 1, negative 1, 0, negative 1. And now that we have matrix P, we have matrix P inverse. The theorem tells us that if we multiply P inverse times A times P, which in this case means negative 1, 0, negative 2, 1, 1, 1, negative 1, 0, negative 1 times 0, 0, negative 2, 1, 2, 1, 1, 0, 3 times this one I don't have in front of me, but it's right here on the screen. There it is. 1, 0, negative 2, 0, 1, 1, negative 1, 0, 1. Multiply these three matrices together. And the fun thing is we'll get a diagonal matrix, but if we work through this, first row, dot with first column, multiplying the first two matrices together, that'll be 0, 0, negative 2. First row, second column, that'll be 0, 0, 0. And we've got 2, 0, negative 6. All told, that's negative 4. Then on the second row, we've got 0, 1, 1. That's 2. We've got 0, 2, 0. That's 2. We've got negative 2, 1, 3. That's 2. And the third row, we've got 0, 0, negative 1. We've got 0, 0, 0. And we've got 2, 0, negative 3. It's negative 1. Multiply that by our third matrix in this product. And that will give us negative 2, 0, 4. That's 2. 0, 0, 0. That's 0. 4, 0, negative 4. That's 0. 2, 0, negative 2. That's 0. 0, 2, 0. That's 2. Negative 4, 2, 2. That's 0. Negative 1, 0, 1. That's 0. 0, 0, 0. And 2, 0, negative 1. That's 1. And so we get a diagonal matrix. But what I want you to notice is not only do we have a diagonal matrix, that's not my highlighter, that's my highlighter. Look at the entries on that main diagonal. 2, 2, 1. When we set up matrix P, the first column was an eigenvector corresponding to eigenvalue 2. The second column was an eigenvector corresponding to the eigenvalue of 2. And the third column was an eigenvector corresponding to the eigenvalue of 1. That is not a coincidence. Right, so for matrix A with eigenvalues lambda 1, lambda 2 through to lambda n, not necessarily distinct, and linearly independent, corresponding eigenvectors, P1, P2, down to Pn, with matrix P given as P1, P2, Pn in that order, every time the matrix P inverse AP is going to be a diagonal matrix with the eigenvalues on the main diagonal and zeros everywhere else. So there are plenty of different places where working with diagonalization will allow us to simplify calculations involving matrices. And the general process does follow this procedure. Step 1 is look at the matrix that you have. Find its eigenvalues and eigenvectors to determine if it is diagonalizable. Set up the diagonal matrix P, set up the similarity matrix P, and then using that, you know what the diagonal matrix is going to be without needing to go through the calculations. And that's a powerful savings. Once you have that diagonal matrix, you can perform work on it. And it turns out that if you simply multiply both sides of this equation by P and P inverse, you can take whatever you did with the diagonal matrix and turn it back into something done on matrix A. Let me throw that one last conclusion in here before we wrap up for today. I'm going to call this a theorem, but it's really not much of a theorem. All right, but assume that we have matrix A, which is diagonalizable. We found the P and P inverse that give us the diagonal matrix. And notice that if you multiply on the left by P and on the right by P inverse, we get that matrix A is P times D times P inverse. So we can find the diagonal matrix, we can do stuff with it, and we can get back to where we started. With that, I am going to wrap up our discussion on diagonal matrices. Take a look at the practice problems involving diagonal matrices, and I'll see you in the next video.